about the session. Okay, so I have this one. Okay, so okay, so so I think you can see this web page. Okay, so we have some analog to digital converter basic here. Okay, and uh, so okay, I will start the lecture and I will explain. Okay, so I am going to use this website. Okay, to give you the basic implementation idea on analog to digital converter. Okay, so okay, so okay, so I hope you can see my writing. Okay, so we are learning ADC and DAC. Okay, so so now we are focusing on analog to digital converter. Okay, analog to digital converter. Okay, please refer the previous day lecture. Okay, so I have explained and I have given a question to work out also. Okay, so please go through that. Okay, uh, okay, so if you consider the analog to digital converter. Okay, so if we are given an analog signal here. Okay, so this is analog signal. It's like this. Okay, and we will get a digital signal. Okay, digital signal like this. Okay, digital signal like this. Okay, so this the digital signal have the digital signal has only two levels. Okay, maybe high voltage level and low voltage level, maybe 5 volt or 0 volt, like that. Okay, so this high voltage level, low voltage level, we already know that it is represented using a 0 or 1. Okay, so these are 1 0 1 0, like this. Okay, so so this ADC, if we are given an analog signal to the ADC, we will get a digital signal. Okay, the output is a digital signal. So this is the input. Okay, and this is the output of the ADC. Okay, so you can see that so this digital signal can be represented using a bit. Okay, actually the immediate step is, okay, immediate step is some voltage value like this. Okay, some voltage value. Okay, so this pin has some voltage value, high or low voltage value. So high voltage value or low voltage value you can represent as 1 or 0. Okay, so this this pin has a high voltage value or low voltage value. In other words, it has a bit. Okay, 0 or 1 bit. Okay, so this is the ADC normally. This is the ADC. Okay, so if you, so you can see that the immediate step is you can get some parallel pin. Okay, you can get that parallel pin. Okay, but I maybe there are some parallel ADC also. Okay, input is serial. Definitely input is serial, no? Okay, because it is a continuous wave. Okay, so you have the input should be serial definitely. Okay, only one signal we are giving. Okay, but at the output we have to get some several bits. Okay, we have to get some several bits. Okay, so output will be, so I'm talking about the ADC input and output. Okay, don't get confused. Okay, so if you consider the input of the ADC, definitely you should have a serial input. Okay, you should have a serial input. Okay, the signal should be fed serial. Okay, and the output may be serial or parallel. Okay, parallel. Okay, so you can see that immediate step is normally parallel. Okay, but you can convert it to a serial also. Okay, so actually most probably I have seen serial to serial ADC. Okay, that means input is serial. Okay, and output is also serial. Okay, so I have dealt with this kind of uh, serial ADC. Okay, actually I didn't work with the parallel ADC yet. Okay, but maybe parallel ADC also may be there. Okay, parallel means I am refer the output. Okay, output can be a parallel. Okay, so anyway, so immediate step is should be parallel. Okay, because we need to get some bits. Okay, or high or low voltage value. Okay, so here we should have high or low voltage value. Okay, these pin. Okay, so the uh, serial to parallel implementation is easy. Okay, serial to parallel. This implementation is easy and we can understand it very well. Okay, so we will first focus on this one. Okay, serial to parallel. The output we will consider the parallel output ADC. Okay, okay. So I think you could understand what I am telling. Okay, so if you have any problem, please stop me and ask. Okay, okay. So now uh, I told you that in previous week, in previous lecture, lecture 10. Okay, that is the lecture 10. Lecture 10. Please refer that one. Okay, lecture 10. Okay. So in the lecture 10, I have told you that. Okay, maybe some of you haven't gone through this lecture. That is okay at this moment. Okay, but try to understand these things. Okay, uh, so we have talked some parameter of the ADC. One is resolution. One is the resolution. Okay, and other is the input voltage range. Voltage range. Okay, and other parameter is also there, that is the bandwidth. Okay, that is the bandwidth. Supported frequency range, that is the supported frequency range. Okay, frequency range. Okay, so I think these three parameters are the most important parameters of the ADC. Okay, actually if you get a data sheet, okay, you could only see these parameters. Okay, other parameters are not much important. Definitely these parameters are there. Okay, okay. So we have explained what is the resolution, and we have explained what is the input voltage range. Okay, and the bandwidth is always related with the Nyquist theorem. Okay, Nyquist theorem. Okay, so so the maximum sampling rate that the ADC can support will determine the bandwidth. Okay, so that is also I have explained as I can remember. Okay, so this is actually this is based on the maximum sampling rate. Okay, maximum sampling rate of the maximum sampling rate of the ADC. Okay, for example, in Arduino board, Arduino Mega, okay, Arduino Mega, you have ADC, the inbuilt ADC. Okay, there is an inbuilt ADC. Okay, if the inbuilt ADC is not there, we can't use the analog pin. Okay, analog pin, there are some analog pin. No, I think as I can remember, 16 analog pins are there. Okay, so that analog pins are connected to the ADC, inbuilt ADC. Okay, so the maximum sampling rate of the ADC, okay, maximum sampling rate of the ADC, as I can remember, it is 9.8 kilohertz. Okay, so you can check it in the internet. Okay, Arduino Uno, I am not sure actually. The Arduino Uno, definitely the sampling rate is less. Okay, The Arduino Mega has the maybe now new boards may be there, but when I was dealing with the Arduino Mega is the most advanced board. Okay, so it has this sampling rate. Okay, I can't remember. I think you can check in the internet. Okay, so you can check it in the internet. Maybe there. Actually, the calculation is also there. How to calculate this one? Okay, the calculation is also there. To calculate this, you have to get there is oscillator in the Arduino board. Okay, so you have to use the oscillating frequency first. Okay, then Arduino Uno should have a ADC. Okay, because Arduino Uno board in Arduino Uno board also there is analog pins. No, if the analog pins is there, there should be an analog to digital converter. Okay, and if you consider a digital multimeter, okay, digital multimeter, okay, it has, yeah, so there should be if the Arduino Uno has the ADC port, there should be a ADC. Okay, the analog port, if there are analog ports, there should be ADC definitely. Okay, so the calculation is also there, you can check it. Okay, but we are mainly focused on these two. Okay, we are mainly focused on these two parameter, resolution and input voltage range. Okay, so what is the resolution? Okay, what is the resolution? Can someone tell? If you have gone through the previous lecture, I think you know the answer for this one. What is the resolution? That is the number of bits. Number of bits. Okay, number of bits that represent a sample value. Okay, yeah, that is okay. So your answer is correct. Okay, okay. No, I think this is no. Okay, I will come to that point. Okay, so this is not a resolution. Voltage range divided by combination, you will get the minimum voltage that can be detected by a ADC. Okay, can you remember that? Okay, so that is also very important parameter. Okay, so please go through that lecture again. Okay, maybe now you may forgot some stuff there. Okay, that is normal. Okay, so anyway, please go through that one and refresh your memory. Okay, okay. So here the number of bits represent a number of bits that represent a sample. Okay, sample value, voltage value. Okay, voltage value. Okay, in other words, it is the number of bits. Okay, number of bits, number of pin. We have the parallel bits, number of pin. We have it the ADs. Okay, so this represent. Okay, so there are some value 0, 1, 0, 1 like this. Okay, so this represent a sampling value. Okay, so so that is the resolution. Okay, number of bits that represent a voltage value. Okay, so that is the sample value. Okay, and other parameters. So please go through that lecture. Okay, I'm not going to explain it further. Okay, so just understand it. Number of bits that represent a sample value. Okay, that represent a voltage. Okay, so that is enough. Please go through that lecture. Okay, so actually before this one you have to go through that lecture very well. Okay, so you can understand this stuff very well. Okay, anyway, we will try to do this. Okay, and the input voltage range. Okay, the other thing is the input voltage range. Okay, input voltage range. Okay, so input voltage range is the minimum and maximum voltages we can give to the ADC. Okay, so I have told you that ADC can't support, okay, cannot support to the minus voltage cannot support to the minus voltage. This can support only plus voltage, that is more than zero. Okay, the more than zero voltage it can support, minus voltage it can't support. It can't sample the minus value. It can sample, but it can't represent the minus voltage value. Okay, it can't represent the minus voltage value using the bit. It can represent only plus value. Okay, it can represent only plus value. This is also very important point. Okay, only plus value, only plus voltage value. Okay, this is also very important. Okay, so if you want to give a signal, okay, with the minus value, okay, with the minus value, and if you want to send the to ADC, okay, ADC will give the value of this only, okay, only this plus value, okay, this value will cut off. Okay, so if you have get the sample, okay, and if you have go through it another DAC, okay, finally you will get only this plus circle like this. Okay, you will not get this uh, part. Okay, so to get this part, what we can do, can anyone tell? So you use your common sense, use your common electronic sense knowledge. And if you want to sample this value also, so what do we have to get? What do we have to do? I think you have used the signal generators in the lab. Okay, in the lab. Okay, so can you try to think a way to get this part also sampled? Anyone? You have to do something to this signal. What is that? Only two words. You have to give what? You have to give what to this signal? Can anyone answer? Yeah, yeah, maybe. Okay, so your answer may be somewhat approx. It is මොකක්ද කියන්නේ ළඟින් යනවා කියන්නේ. So your answer is not correct, but it is going nearly. Okay, ළඟින් යනවා කියන්නේ. So what we have to do? So you can see that if you want to get this one also, okay, if you want to get this one, if we shift this signal upward, okay, if we signal upward by this value, okay, let's say that this is 5 volt, okay, so if I shift this value by 5 volt, I will get this kind of signal. Okay, now I have the shifted signal, okay, the amplitude shifted signal. Okay, so if you write, so you tell that amplitude, okay, and again another words you have to tell that that is amplitude shifting actually. Okay, ඒකයි මම කිව්වේ ළඟින් යනවා කියලා උත්තරය. Right, so if you have given amplitude shift to the signal, it can go, okay, so we can move this minus part also to the plus part, to the plus value. Okay, and what is this called? What is this called? In signal generator you have this facility. What is that? In signal generator you have this facility. You can create, you can get the value and you can shift it above. So what is that? You can shift this, actually you can shift this in many ways. Okay, using the power supply also you can shift this value. if you have this kind of signal, okay, let's say that this is 5 volt, okay. So if you connect a 5 volt to this signal, okay, if you connect a 5 volt to the signal serially, okay, you can shift this up, down, up way, okay. So that is called DC offset, no? That is called DC offset. Can't you remember? Maybe you have used this facility in the signal generator. Haven't you used DC offset function? Yeah, you have used, okay. So you can give a DC offset, okay. Actually, you no need to give the DC offset if you have a power supply. If you give a 5 volt or 6 volt with that connected with this signal generator seriously, again you can shift the signal, okay. Again you can shift the signal. So there are many ways to give a DC shift, okay. So you have to give the DC shift to the signal and you have to upward it to the plus side. Then you can send it through a ADC. Then you can get the whole waveform. You can get sampled whole waveform, the complete waveform. Okay. Otherwise, you will get only a plus value. Okay. So this one is also very important point. Okay. Okay, so what is the input range? Okay, so what is the input range? Normal input range is 0 to some maximum value. Okay, so it is depend on the ADC. Some ADCs are 12 volts, some ADCs are 5 volts, 7 volt, 8 volt, like this. Okay, so that is the normally the so this maximum voltage depend on the ADC type. Okay, so that is the input range. Okay, 0 to some maximum voltage value. Okay, so that is the input voltage range. Okay, and we have used this resolution and input voltage range, and we can find the minimum uh, voltage level that can be that can be uh, that can be catched. Okay, that can be catched or interpret. Okay, that can be interpreted by the ADC. Okay, minimum voltage level. How we can find the minimum voltage level? Okay, so this is voltage level minimum. Okay, minimum voltage step actually. This is step. Okay, so how we can write? We can find it. So if you have the range V max to some V min value, most probability is 0. Okay, it is divided by, okay, so the resolution, number of bits, okay, number of bits that the sample uh, can can represent. Okay, so let's say that there are some n bits. Okay, so if there are n bits, how many voltage value you can represent? If there are n bits, how many voltage value you can represent? I have told you that resolution is the number of bit. Okay, resolution is the number of bit. Okay, and so that number of bit will represent a voltage value. Okay, for example, let's say that your ADC resolution is 4. Okay, your ADC resolution is 4. Okay, then that means you have, let's say that it is 2. Okay, it is 2. Your ADC resolution is 2. Okay, then uh, so using 2 bits, you are represent a voltage value. Using 2 bits, you are representing the voltage value. Okay. Yeah. Okay. So that is the answer. Okay. Okay. So how many voltage value you can represent using these two bits? How many voltage value you can represent using these 2 bits? Can another one answer? So yeah, that is 4. Okay. So So you can see that there can be 1 0 0 1 1 1 0 0 like this. Okay, so this will be a voltage level, this will be a voltage level, and this will be a voltage level, this will be a voltage level. Okay, so you can represent 4 voltage level. Okay, 4 voltage level definitely. Okay, 4 voltage level. Okay, so so these are the number of voltage level you can represent using 2-bit resolution ADC. Okay. If it is 4 bits, if it is 3 bits, how many voltage level you can represent? If it is 3 bit. How many? Yeah, yeah. Other one? That means you will have 8 combination, no? 0 0 0 0 0 0 0 1 1 0 0. Likewise, you have 8 combination. That means 2 to the power 3 combination. 8 combination. So you can represent 8 voltage value. Okay. So if your resolution, if your ADC resolution is n bits, how many voltage level you can represent? Yeah, that is 2 to the power n. 2 to the power n voltage level you can represent. Okay. So there are 2 to the power n combination or voltage level. Okay. So if you divided the full range by 2 to the power n, that means number of combination. Number of combination or number of voltage levels. Voltage levels that can be represented by a ADC. Okay, so you will have the minimum voltage level. Okay, so only that voltage level can be interpreted by the ADC. Okay, for example, if you have 2 bits, okay, and your voltage is 4, your maximum voltage is 4. Okay, what is the minimum? So this is the resolution. This is the resolution, 2-bit resolution, and there are 4. This is the maximum voltage that can be given to the ADC. Okay, so what is the minimum voltage value you can interpret? What is the voltage minimum value you can interpret? What is the minimum voltage value you can interpret? Please tell me. So this is the maximum voltage. Let's say that it is 0 to 4. Okay. Normally it is 0 to 4. Okay. It will not be a minus value. Okay. In every time it will be a plus value, plus range. The ADC input range is plus value. Okay. Not a minus value. Okay. Most probably it is 0 to 4. Okay, not it is the minimum is 0 and maximum can be any value. Okay, let's say that here it is 4. Okay, so your voltage range is 4 minus 0, and how many combination? 4. Okay, that means you can represent, the minimum voltage that can be interpreted by the ADC is 1 volt. Okay, so you can interpret 1 volt, 2 volt, 3 volt, and 4 volt. Okay, only these 4 voltage level you can represent. Okay, so you can use 2 bits here. You can use another 2 combination here. You can use another combination here, and you can use another combination here. Okay, so this ADC can represent only 4 voltage level. Okay, and 1 is the minimum one. Okay, so you can see that always there is a 1 step. Okay, 1 voltage step to the other level. Okay, So if you resolve if you increase the resolution, let's say that your resolution is 3, then this is 8. Okay, the combination is 8. Then the minimum voltage value will be 0.5. At that time, you can represent 0.5, 1 volt, 1.5 volt, 2 volt, 2.5 volt, 3 volt, 3.5 volt, 4 volt, so on. You can represent 8 voltage level. Okay. Okay, so that is the resolution. Okay. Now we will go to the implementation part. Okay, because these things we have already discussed in the lecture 10. Okay. So I will quickly go to the designing part. Okay. Okay. So I will give you an example. Okay. I will give you example. Okay. So we have ADC. Okay. We have ADC. Let's say that it is 2-bit resolution ADC. Resolution ADC. Okay. And we have, okay. So for the easiness, I get 2 bits. Okay. And let's say that we have the maximum voltage, the maximum input voltage is 8 volt, and the minimum input voltage is 0 volt. Okay. Okay. Then find how many voltage levels we can represent. And what are the voltage level? What are the voltage level? Voltage level we can get, we can represent. Okay, how many voltage level and what are those voltage level? Okay, so tell me, take 5 minutes and tell me. Okay, so the V min level. Okay, so you have to find this one, and what are the voltage value? What are the voltage value? That's okay. So tell me these things. Take 5 minutes and tell me. Okay, so I think I get some answer. The answer is correct as I can see. Okay, so you can see that 2-bit resolution. Your ADC is 2-bit. Okay, that means your ADC is like this. Okay, so definitely input. This is the input. Okay, this is the input. Input is 1 pin. Okay, and you will have 2 pin output. Okay, so these are the 2 bits actually. Okay, so resolution is the number of pin. Okay, number of pin. This is the resolution. Okay, and so your ADC is look like this. Okay, ADCs look like this. Okay, so you can see that you can represent, you can set this pin to 0 and this pin to 0, or this pin to 0, this pin to 1, this pin to 1, and this pin to 0, and this one, this to 1, and this to 1. Okay, so that means you have 4 combination, that is 0 0 0 1 1 0 1 1, like this. Okay, so you have these 4 combination. Okay, so how many voltage value you can represent? That is 4. Okay, 4 voltage value you can represent. Okay, that is depend on the resolution. So this is depend on the resolution, number of voltage value. Okay, and what are the voltage level we can get? Okay, so what are the voltage level? What is the minimum voltage level we can get? Okay, so to find the minimum voltage level, okay, we mean, okay, we have to divide the range, input range, voltage range, minimum levels. Okay, minimum level, minimum step. Let's say that it is minimum step. Okay, so we have to get the full range, that is 8 volt minus 0, that means 8 volt, divided by number of combination. Number of combinations are 4. 1, 2, 3, 4. Okay, so the minimum voltage step is 2. Okay, step is 2. Okay, then what are the voltage levels we can represent here? We can get, what are the voltage level we can get from this ADC? Please tell me, what are the voltage level? Yeah, actually 0 we can't. Okay, we can represent 2, 4, 6, 8. Okay, so these are the voltage level we can represent. Okay, okay, so these are the represent voltage level. Okay, okay, so so you know that. Okay, so this is how it happened. Okay, so we have a ADC. Okay, we have a ADC. Okay, and the input is serial, and output we have 2 pin. Okay, we output we have 2 pin. Okay, let's say that you are sending a signal like this. Okay, so first you have to sample this signal. Okay, you have to sample this signal. Then this sample is a voltage value. Okay, these are voltage value. These samples are nothing but voltage value. Okay, so you can convert this voltage value into a binary value. Okay, so let's say that, okay, let's say that this voltage value is 2 volt. Okay, then you can convert this to 0 0. Okay, like this you can convert it to 0 0. Let's say that this voltage value is 3 volt. Okay, so you can't represent the 3 volt because you can't interpret the 3 volt using this ADC. Okay, so you have to approximate this 3 volt to 4 volt or 2 volt. The minimum, the encodable, that is the word. Okay, encodable voltage value you have to approximate. Okay, so this is we call quantizing. This is we call quantizing. Okay, so you have to sample the signal. That means you are getting some voltage value. Then you have to quantize them. That means you are going to approximate them to an encodable value. Okay, encodable voltage value. In this case, so if you have sample voltage 2, 3, 4, 5, 6, 7.5 like that. Okay, so you have to approximate these to a encodable level. Okay, so encodable levels are 2, 4, 6, 8 in this case. Okay, so you can represent this 2, you can represent this 3 by 4 or 2. Okay, you can represent this 4 directly, you can represent this 5 from 6 or 6 or uh, from 6 or 4. Okay, from 6 or 4, and you can represent this 7, you can represent the 6 itself, and you can represent this 7 5, encode this 7 5, represent this the approximate this 7 5 to maybe 8 volt. Okay, then you can encode this voltage level. Okay, so you have to quantize them or approximate to a encodable voltage level so that you can encode them into a bits. Okay, so that is we are doing in the quantization. Okay, now don't worry about that part. Okay, so if you can't understand them very clearly, you can refer my lecture 10, then you will understand these things. Okay. So now we will try to implement this. Okay. So that is the today parts actually. Okay, now we are going to implement this. Actually, if you have watched the lecture 10, okay, we can skip all these things and we can start from here. Okay, we can start from here at the implementation. Okay, implementation. But if I am talking about the implementation without this knowledge, you can't understand these things. Okay, so I had to explain that one, and it is almost take about 1 hour. Okay, so you can see that if we are not aligned with the lectures, okay, our time will be wasting. Okay, so try to please align with the lecture. Otherwise, we can't go up to the intended level. Okay, okay. So it is actually the that is a disadvantage for you. Okay, if we can't, you think, but I know that as a student, you are thinking it may be an advantage. Okay, because you will get some few things for the exam. Okay, so for the exam I have to give the completed part. No, I can't give you the additional part for the exam. Okay, so it may be easy for you. Okay, if we couldn't cover all the content, it may be easy for you. Okay, because your exam will be easy. The amount of stuff you have to keep remember may be less. Okay, but it is a disadvantage in other way. Okay, uh, but you can avoid this disadvantage. Okay, by doing the works. Okay, by doing the practical things, and you can get the knowledge actually by reading the books and by doing some experiment in the labs. Again, you can get the knowledge back. Okay, so at least try to do that one also. Okay. Okay, anyway, so we will go into the implementation part. Okay. Okay. So before going to the implementation part, okay, so I will go to that one. Okay. So can you see this? Okay. So can you see my website? I am in a website that now. Can you see that one? I think you can see now. Okay. Yeah, thank you. Okay. So actually, so using this circuit, we can build a ADC very easy. Okay. Using this circuit, we can build a ADC very easy. Okay. So please tell me, are you familiar with this circuit? Are you familiar with this circuit? Can anyone feedback? Maybe you have familiar with this. Maybe not. I don't know. Have you learned about op amps? Yes, thank you. Okay. So you have learned about the op amps. Okay. So this LM3399 is op amps actually. Is operational amplifier. Okay. So I think so maybe you are not familiar with this circuit. Okay, but you are familiar with the basic circuits of the amplifier, no? Operational amplifier. This is plus and this is minus. Okay. So here we have a resistor like this, and it is here. Okay. And there is a resistor also like this, no? Okay. And there may be a resistor here also. Okay. So I can't remember the exact one. Okay. So normally this is the standard amplifier circuits, no? Okay. Using the amplifier. Okay. So you may be familiar with this one. Okay. And I think you know how to find the voltage here using this resistance. Okay. So this voltage can be represented with this resistance here. Okay. And this as well as the input resistor, input voltage. Okay. Okay. So I will, so actually I also couldn't much. I have to refer the knowledge again. Okay. I can't remember how we can calculate them, but I think for this stage, but for this stage, we no need to go through in that level. Okay. So, so we call this a comparator circuit. Okay. We call this a comparator circuit. Okay. So, what is actually we are doing here is, okay. So if we have this kind of operational amplifier, okay, okay, and we have to connect it with the input, definitely, okay, okay, like this, okay. So this is plus and this is minus, okay. Let's say that we are giving some value here, voltage value here, okay. Let's say that it is V plus, and if you are given a voltage value V in here, okay. So if VF is, okay, so this voltage, okay, okay, I will refer this as reference voltage, and so this is the reference voltage Vref. Okay, let's say that the voltage given to this plus P, that is voltage reference, voltage ref. Okay, and let's say that this is voltage input. Okay, so these two are input voltage. Okay, and uh, we we represent this as reference voltage. Okay, and the most important thing you should understand is, okay, this if this V ref is greater than V in, okay. In other words, if your voltage difference is in this direction, this is the high voltage and this is the low voltage. So it is in this direction. So this direction, this you have a plus value, plus voltage value. Okay. And if V in is less than V ref, here you have a minus voltage value. Okay. So I think you can interpret this, okay, using the basic operation amplifier circuits. Okay. So try to interpret it. Okay. Okay. So okay. So if V ref is greater than V in, okay, so you have a high voltage value here. You have a high voltage value here. So here the output will be high. Okay. Let's say that it is 1. Okay. And V in is less than V ref, you have a low voltage value. Let's say that it is 0. Okay. I'm correct, no? Let's see this. Okay. V in, yeah. V in is less than V ref, the output is low. Okay. The output is low. That means it will be a, most probably it will be a minus voltage value. Okay. So it is a low value and we can represent as off. Okay. And if V in is greater than V ref, it is the other way around. No? It's the other way around. No? If the V ref is greater than V in, V ref is greater than V in, it is off status. And V in is greater than V ref, it is on status. Okay. So we will take that one. Okay. Anyway, try to interpret it using the op amps. Okay. It is, we no need that knowledge into this level. Okay. Anyway, I'm not going to explain it. Actually, I also can't remember that one. Okay. How it get. Okay. So anyway, uh, if the V ref is greater than V in, say that V in is greater than V ref, it is high, no? It is high. And V in is less than V ref, it is low. Okay. That means this is 1 and this will be 0. Okay. So, so you can define it in this way. Okay. So try to interpret it as using the op amps. Okay. As a homework. Okay. So So normally this is the this is the standard way. Okay. So I will use the, so maybe you can represent in other way around also. Okay. It also will give you a correct answer. Definitely. Because the 0 and 1 you can represent in any way. You can represent 1 to the lower level, and you can represent the 0. You can assign the 0 for the higher voltage level, and you can do the other way around. Okay. So both things are okay. Okay. So anyway, uh, so we will go through this one. Okay. Because here we have that one. No? When the V in is V ref is greater than V in, you have off. V ref is less than V in, you have on. Okay. I have correctly write it. No. V ref is less than V in, it is high. V in is V ref is greater than V in, it is low. Okay. So we will take this one. Okay. Now, okay. So we called it a comparator. Okay. If you are using op amps in this manner, it will, it will, it is a comparator actually. It is compare, okay, it compare two voltage level. It is comparing two voltage levels. Okay. Okay. V ref and V in. This voltage and this voltage, it is compare, and it give a output according to the comparison. Okay. The high voltage value or low voltage value. Okay. So that is the things you should understand here. Okay. Okay. Now I want to, okay. So now, uh, now I am going to design this ADC. I am going to design this ADC. Okay. I am going to design this ADC. Okay. So, so I will write the specification here again. Okay. So the input V max is 8 volt. Okay. And the output, sorry, the the number of voltage levels, number of voltage level is 4. Okay. Because resolution is 2. Okay. We can represent only 4 voltage. Okay. And what are the voltage we can represent? That is 2 volt, 4 volt, 5 volt, sorry, 6 volt, and 8 volt. Okay. So these are the exact voltage level we can represent. These are the exact voltage level we can represent, or these are the exact voltage level. Okay. Voltage level we can decode, we can encode, we can encode. Voltage level we can encode. Okay. So if you have any voltage level between this one, you have to quantize or approximate it to a exact voltage level. That is quantizing. Okay. That is we need, that is why we need the quantizing in the ADC process. Okay. Okay. Now these are the voltage level. So you can see that you have 4 voltage level. Okay. You have 4 voltage level basically. Okay. Now tell me how many voltage level we have to compare. We have to compare 4 voltage level, because we have 4 voltage levels here. Okay. These are the encodable voltage level, and in our ADC we have 4 voltage level. Okay. So we have to compare 2 voltage level. Okay. For the comparison, you can use this comparator circuits. Then how many comparator circuits we need? We have to compare 4 voltage levels. So how many comparator circuits we need? How many comparator circuits we need? Yeah, that is 4. We need 4 comparator circuits because there are 4 voltage levels. Okay. So I can have 4 comparator circuit like this. Okay. I can have 4 comparator circuits like this. Okay. 4 comparator circuit like this. Okay. So This will be plus and this will be minus. This will be plus and this will be minus. Okay, this will be plus and this will be minus. This will be plus and this will be minus. Okay, this will be minus. Okay, so there are four voltage. Okay, now what is the maximum voltage level I can input? That is 8 volt. Okay, that is 8 volt. Okay. So we have to, so now you have 2 volt, 4 volt, 6 volt, and 8 volt. Okay, you have 8 voltage levels. Sorry, 4 voltage level. Okay, so you can have, you should have 4 comparator circuits to compare this 2 voltage. Okay, so now let's say that, okay, we are going to compare the 8 volt using this comparator, and you are going to compare the 4 volt, 6 volt using this comparator, and you are going to compare 8 volt, sorry, 4 volt using this comparator, and you are going to use 2 volt using this comparator. Okay, so this comparator is 8 volt, this comparator is 6 volt. This is going to compare the 4 volt. This is going to compare the 2 volt. Okay, so what are the voltage value we have to give to this ref? Okay, let's say that this is 1. No, this is 3. This is 1. This is 2. And this is, sorry, this is 2. This is 1. And this is 0. Okay. So this is Vref 3, Vref 2, Vref 1, and Vref 0. What are the reference voltage values we should give to this reference voltage? What are the voltage value? Very easy. Tell me. So you are going to compare the 8 volt. Okay. So if the 8 volt is here, you need to compare this. It is the if so this will, so you are going to give a voltage here. Okay, voltage here, and you want to compare it. It is greater than 8 volt or less than 8 volt. Okay. So what is the reference voltage you should give to here? And what is the voltage level you should give here? And what is the voltage reference you should give here? And what is the reference voltage you should give here? What is the voltage value you should give here? Yes, that is 8 volt. Here you have to give the 8 volt. Here what you have to give? You are going to compare 6 volt. So you have to give the 6 volt here. Here you are going to compare the 4 volt. You have to give the 4 volt here. You are going to give a 2 volt. You can give a 2 volt here. Okay. So this is the this is the voltage. Okay, we have to give the reference voltage. The exact voltage level we can only decode. Okay, so those voltage level we have to give as the reference voltage to the comparator. Okay, so what is the technique we can use to give this voltage? You can use any technique. You can use a Zener diode, you can use a power supply, different power supply, or you can use any method. Okay, but are there any method comes to your mind to give the voltage like this, to divide the voltage like this? Do you have any suggestion? So we have to divide. Okay, so you can give the separate voltage, no problem. Okay, and if you want to divide this voltage and give the separate point, what you can do? Anyhow, you have to give the voltage, this voltage level. Okay, that is the requirement. Yeah, you can use a resistor. Okay, what is that called actually? You can use resistor circuit. What is that? What is that circuit called? Use the engineering words. What is that called? So in our electronic circuits, we have to use this in many kinds. So if we have a two resistor like this, okay, and if you have given a voltage here, okay, and if you get the voltage here, you have a certain voltage. Yeah, that is the voltage divider. Okay, so this is the voltage divider. Okay, voltage divider using the resistor. Okay, so we can make the voltage divider using the Zener diode also. Okay, you can use the Zener diodes and you can divide the voltage. Okay, and you can use the voltage regulators. There are some voltage regulators. No, can anyone remember what are the IC voltage regulators we have in our labs? Can anyone remember? Regulate IC is starting with 78 or 79. No, can you remember that? 7805, 780, 7812, 7809. Likewise, we have some regulate IC. Okay. So if you are given a voltage, so regulate IC is like this. Okay. Like this. So if it is 7805, you can give the 12 volt to the input. Okay. So this will be the minus and plus maybe. You can give it to 12 volt and you can get the 5 volt regulated 5 volt output. Okay. And if it is a 789, you can get a 9 volt. Okay. And what is 79? Can you explain? Can you remember that? What is the 79? This will give you the minus voltage. Okay. So if it is 7905, this will give you the minus 5. Okay. So these we have in our labs. Okay. Haven't you used these? Haven't you used this? So you have to use this, okay? Otherwise, you can't learn the electronics. If you learn the theories, it is not electron, okay? If you learn just these things and if you just write the exam, it is not the electronic, okay? You have to do these practical things, okay? So please come to the labs if you have time and I will give you some voltage regulator and you can check them, okay? And also try to use the DC shifting one. These are very important, okay, I think. Okay, so anyway, what I want to tell you is that to give a certain voltage to this point, you can use the voltage divider, resistive voltage divider. You can use Zener diode, or you can use regulators, voltage regulators. Okay. What are there any other methods? I can't. So other methods not come to my mind. Okay, but there may be other methods also. Okay, so here we can use a voltage divider. Okay, in many cases we are using the voltage divider here. Okay, so so can you so if I do like this, okay, if I do like this, okay, so 8 volt is here. Okay, we have a 8 volt and here we have a 0. Okay, and if I use 4 resistor, okay, now this is 6 volt, okay, and this will be 6 volt, and this will be 4 volt, and this will be 2 volt. Okay. Okay. So what are the resistor value I have to use? Can anyone tell me? What is the resistor value I have to use here? What are the resistor value I have to use? What are the resistor value I can use? Yeah, very good. Okay, you can use any same four resistor. You can use any four same resistor. Okay, same resistor. Okay, I'm not going to explain this voltage divider. You can use the Ohm's law and you can understand this. Okay, so if you use any volt resistor like this, okay, okay, but when you are doing when you are implement a circuit, you have to care about the resistor. Okay, because this resistor will limit the current. Okay, this resistor will limit the current. The resistor value will limit the current. Okay, so to give a proper current, you have to care about the resistor. Okay, you have to care about the resistors. Okay, so in this stage, if you think that if we are given any four resistor, equal resistor, this will be a voltage divider. Okay, so voltage will here is 8 volt. Okay, and here you will have 6 volt, and here you will have 4 volt, and here you will have 3 volt. Okay, so what you have to do is that you can put the Ohm's law, V equal IR to this one, to the whole circuit, and again you can use V equal IR to find the specific voltage level. Here, let's say that it is V3, V2. This is reference, okay? Vref3, Vref2, Vref1, and Vref0. Okay? So you can use again V equal IR, okay? And this R, in this case, R is for R, and other cases, R will be plus, okay? But the same I, okay? Because this is a serially connected resistor. Okay, so I is same. Okay, so you can use the Ohm's law and find the voltage value here. If you can't remember this voltage divider, okay, do that with you. Okay, so now that is okay. Okay, we have given the uh, give the uh, appropriate voltage levels. Okay, now if you give a V in, if you give a V in to this one, okay, and if you connect it to here also, this one, and here also this one and this one. Okay. So I have give the V in. Okay, I have give a V in, and this is my voltage. Okay, this is my voltage, and this is my analog voltage. Actually, this is my analog voltage. This may be any value from 0 to 8. Okay, this V in can be any value to 0 to 8. Okay, it can be any value to 0 to 8. Okay, correct? Do you have any issue? This is my ADC. Okay, now I am going to uh, going to implement this ADC. Okay, so I should have one input. Okay, and input I have to give the V in, so it will be my analog signal. Okay, and now I am going to give my analog signal to this pin, and I connect that analog signal to this V in pin. Okay, this is V in 1 pin 3. Okay, and this is V in 2. Okay, and here also I have connected, it is V in 1, and here I have connected, it is V in 0. Okay, so I have connect my analog voltage to this input pin minus pin of the comparator. Okay, now tell me, if you are given 0 voltage here. Okay, now let's say that you are given 8 voltage. Okay, so we will start from the maximum one. Okay, so the maximum input is 8. Okay, so your signal is like this. Okay, so you are given a signal like this. Okay, so your input signal V in, okay, V in, let's say that your V in is like this. Okay, you are given a V in like this, analog signal like this. Okay, so this is 8 and this is 0. This is a voltage level. This is a voltage level. Okay, and this is a time. Okay, so you are given. So you are given the voltage like this. Okay, So it is analog signal. No, this is analog signal, analog voltage. So you have infinite number of amplitude level between this 0 and 8. Okay. Okay. Now say that. So let's say that this is our first sample. Okay. This is our first sample. So this is the first voltage level. Okay. That is 8 volt. Okay. So if the 8 volt is here, okay, what are the value we have here? Okay. Let's say that this is D0. I write it as D1. Okay, let's say that I will use the same notation. You can use any notation, okay? But here it is D1, D2, D3. Here you are using only 3 comparators. Okay, anyway, we will see. Okay. Okay, let's say that this is D0, D1, this is D2, this is D3, and this is D4. Okay. So these are the value. Okay, these are the comparator value. Okay, so tell me, if you are given 8 volt, okay, 8 volt, okay, if you are given 8 volt, so if you are given 8 volt, you have a value D1, you have a value at D2, you have a value at D3, and you have a value at D4. Okay, so what are the values? You can use 0 and 1, so you can use this condition. Okay, this one. Okay, you can use this one. Okay, what is this one? You can use this one. Okay. Okay. So for that one, you have to use this condition. Okay. I will put it here. Okay. We write it here. Okay. Okay. So you know that Vref is greater than V in. You have 0 at the output. Vref is less than V in. You have 1 at the output. Okay. Vref is less than V in. You have 1 at the output. Okay. So tell me D1, D2, D3, and D4. So use this condition. Use this condition. And the 8 volt is here. So you are given 8 volt. Okay. So tell me what are the value at D1, D2, D3, and D4. Okay. Okay, I got answer. Okay, let's see. Okay. So I will check it one by one. Okay. So here, this voltage is 8. Okay, this voltage is 8. Okay. And if you are given 8, this one also 8. Okay. And Vref and V in is equal. Okay. So there should be a 0 value here. Okay. V in and Vref equal. Voltage difference is 0. So you have a 0 value here. Okay. So this is D4. In D4 you have 0. Okay. Let's say that D1. Okay. So you have 6 volt here. Okay. And 8 volt here. So V in, now V in is greater than Vref. V in is greater than Vref. Okay, so it is in this condition. So we have 1 here. Now if you consider this one, here it is 4. Okay, here it is 4. Okay, so this is 4 and this is 8. Okay, so you can see that V in is greater than ref. Okay, so here this one is also 1, this one is also 1, correct? Okay, so you have this one. Okay, D4 1 and others are 0. D4 1, others are 0. Yeah, if you consider the other way around, it will like this, no? It is D4 0 with the D1 maybe 0 and D4 will be 1. Okay, but I think according to the yeah, okay, thank you. Okay, according to the condition we consider, okay, so the bit pattern should be like this, no? 0 1 1 1. Okay, so you can see that now 8 volt is converted to this, like this. Okay,
Excuse
okay,
me, sir.
yeah.
සර් එතකොට D4 එක මේ එක වෙන්නේ නැද්ද කොයි ලාක?
අපි බලමු සමහරට වෙන්නේ නැති වෙයි නේ. D4 එක වෙන්න විදියක් නැහැ. මොකද 8 volt නේ maximum එක. අපි 8 volt වඩා වැඩි දුන්නොත් තමයි D4 එක වෙන්නේ. ඒ වුණාට අපිට ADC එකට දෙන්න පුළුවන් maximum value එක තමයි 8 volt කියලානේ අපි ගත්තේ. එතකොට අපි 9 volt වගේ දෙන්න හොඳ නැහැ නේ. ඒකින්ද D4 එක එන්නේ නැති වෙයි එක. හරි අපි බලමු. මමත් මේක උග කාලෙකින් කරන්නේ. මටත් එහෙම මතක නැහැ කොහොමද දෙන්නේ කියලා. හරි. මම හිතන්නේ මම ෆයිනල් ඉයර් ප්‍රොජෙක්ට් එක කරනකොට තමයි මේක කරේ දැන් බරහනකට කලින් නේ. අවුරුදු 12කට විතර කලින්. ඒකින්ද මටත් හරියට මතක නැහැ. Anyway, we will try, okay? So the important thing is the logic. Okay, the logic we are using here. Okay, so you can understand the behavior of the ADC, implementation of the ADC. Okay, okay. So let's say that now it is 8 volt. Okay, okay. Now let's tell me that what happen if the voltage is 7 volt. What happened? The voltage is 7 volt. Let's say that you have take another sample here, and it is 7 volt. Okay. So what is that? So what is the what is the bit pattern you will get? Yeah, that is the same bit pattern. No, you will get, if it is 7, you will get again 1110. Okay, if it is 7.5, 7.4, 7.3, any value, you will get, okay, 7.9, any value, you will get, and also 6.9, no, 6.2, 6.1. If you consider this value also, you will get 1110. Okay, so you can check it. Okay, for example, let's say that V in is now 6.4. Okay, so V in is 6.4. Okay, so here V ref is 8 volt, V in is 6.4. Okay, so V ref is greater than V in, so you will have 0 here. Okay, so D4 will be 0 because V in is greater than V ref. Okay, now 6.4. Okay, so now here the V ref is 6, but we have 6.4 here. Okay, 6.4 here. That means V in is greater than V ref. That means this status. V ref is greater than V in. Okay, so here you will have happen. V ref is, yeah, sorry, V ref is less than Vn. Okay, sorry, I have I have told mistakenly. Okay, okay, I will start at the beginning. Okay, so if we have 6.4 voltage, 6.4 voltage, 6.4, what happened? So here you have 6.4. Okay, here you have 6.4. In V in you have 6.4. Okay, so here you can say that V in is less than V ref. Okay, V in is less than V ref. Okay, V in is less than V ref. Okay, so it will be 0. So your D4 will be 0. Correct. Okay, D4 will be 0. And if it is 6.4, 6.4, V in is greater than V ref, because here it is 6.4 and here you will have 6. Okay, so V ref is less than V in. So you will have 1 here. It is correct. And D2 you will have the 1 here because here you have 4. This is 6.4. So V in is greater than V ref. Here also 2, and V ref is V ref is 2, and V in is 6.4. So it is V in is greater than V ref. Again, you will have 1. Okay. So that means from 8 to 6, up to 6, from 8 to up to 6, you will get this pattern. No? This pattern. So that means 0 to 8, 0 to 7 volt, you will get this pattern. No change. Okay, correct? Are you okay with that? Or if you have any problem, please ask. Okay. Okay, now let's say that means if you are getting any sample up to 6, okay, all this sample will quantize to 8 volt. No? All this sample will quantize to 8 volt. Okay, the upper volt or approximate to 8 volt, and you can get the 8 value. Okay, up to this level. Okay, now let's say here you have a sample 6. Okay, now you have a sample 6 volt. Okay, now tell me what is the bit pattern you will get. You have 6 volt here. And what is the bit pattern you will get here? Okay, we will see. Okay, so here we have 6. Okay, here we have 6. Definitely D0 will be 0 because it is greater than. Okay, D0 will be 0 because V in is less than the reference voltage. Reference voltage is 8 and input voltage is 6. Okay, and for the the third comparator D3, okay, V ref is 6 and the input also 6. Okay, so you don't have a voltage difference and you will get a 0 there also. Okay, and what at D2? So here you have 4 and you have 6 here. Okay, and you will get 1 here because V in is greater than V ref, and here in this case so also V in is greater than V ref. So you will have 1 here. V in is greater than V ref. Okay, so you will have this combination. Okay, and what happen if you have 5.9, 5.8, 4.8, 4.9, 4.2, 4.1, and 4 up to 4? What happened? Okay, so up to this is up to 6. Okay, this is up to 6 actually. So 6 to 4, what happened? The uh, the the 6 is not included here. Okay, less than 6. Okay, so here the 6 is included. 6 to 4, but the 4 is not included up to 3.9999. Like that. Okay, so up to here, if you are not comfortable, I will write it as 7. Sorry, it is actually 6.00001 value. No, it is near to 6. Okay, I can't write that value. Okay, so here please note that this is not equal to 6. Okay, 8 to 6. Okay, that is why I write it in red. Okay, so 6 volt is not included here. Okay, this 6 volt up to 4 and 4 volt is not included here. Above 4 volt. Okay, above 4 volt, 0.4.00 like that. Okay, and tell me, if you are given 4 volt, what happened? If you are given 4 volt, what happened? Actually 4 volt to 4 volt up to 2 volt. What happened? You will get D4 definitely 0, D3 definitely 0, and at D2, okay, D2, here you will have 4 and here you will have 4, and this one also will 0. But here you will have Vref 4 and Vref 2, V in 4. Okay, that means V in is greater than Vref, you have 1 here. Okay, and what happened if you are given 2 volt? 2 volt. This one also will be 0. No, correct? D2, because here you have 2 volt, here you have 2 volt. Okay, so you will have the same value and you will have the 0 here. And these are definitely 0, no? Because V in is less than Vref. If the V in is 2. Okay, so I am talking the V in here. Okay, okay, so it is from 2 to 0 volt up to 0 volt, you will get this binary value. Okay, so now tell me, you have 4 different binary levels. Okay, you have 4 different binary levels. No, so you can represent these 4 voltage levels 8, 6, 4, 2 by 4 binary values. Okay, but here you have 4 digits. Okay, okay, do we require 4 digits? Do we require 4 bits to represent 4 levels? Tell me, do we need 4 bits to represent 4 level? For combination, do we need 4 bits? Tell me. No, then how many bits we need actually? To represent 4 level, how many bits? Yeah, no. To represent 4 level, do we need 3 bits? If we have 3 bits, you can represent 2 to the power 3 levels. That means 8 levels. To represent 4 levels, how many bits you need? You no need 3. How many levels? How many bits to represent 4 level? Please tell me. To represent 4 levels, how many bits we need? Here you have only 4 levels, no? 8 up to 6, you have 1 combination. Okay, and the 6 is not included here. And 6 to 4, 4 is also not included. You have 1 combination. 4 to 2, you have another combination. 2 to 0, you have another combination. You have 4 combinations. Okay, you have 4 combinations. Then how many bits you need? Here we use 4 bits, but we don't need 4 bits, no? Using 4 bits, we can represent 16 level. But here we only have 4 levels. So how many levels? Hello, can you hear me? Am I audible? Okay, then tell me how many bits we need. Very simple question. Yeah, 2 bits. We can have 2 bits, no? So we can represent this 4-bit combination using the 2 bits. Okay, like this, you can represent this by 1 1. You can represent this one using by 1 0. You can represent this using 0 1, and you can represent this using 0. So you have only 2 bits to represent this level. Okay, so okay. 2 bits, no? So that means it is a 2-bit resolution. Okay, it is a 2-bit resolution. So we are designing 2-bit resolution. So you can use 2 bits. Okay, so now another part is that, so there are 4 levels, no? 4-bit combination, and you have to convert them into a 2. So that one, okay, so here you need to have a 4 to 1 mapping, 4 to 2 mapping circuit. Okay, so this is a 4 to 2 mapping circuit. And I think this is also called as 4 to 2 encoder. I am not sure this word, okay. And I think it is also called as 4 to 2 encoder. Actually, you can construct this encoder using XOR gate or XNOR gate. I can't remember exactly. Maybe XNOR gate, using XNOR gate and using transistor. You need the transistor also here. Okay. You need to have, yeah. Okay. So this is actually 4 to 2 encoder. Okay. So this implementation we are not going to look at. This implementation, maybe you have done this in your first class. Haven't you done this? 4 to 2 mapping. It is just like a multiplexer. But you can implement this using the logic. Okay. Very easily you can implement this using the logic. Okay. No need the transistor, I think. Here. So this is, can you see this? This is XOR gate. Okay. So you can use XOR gate. Okay. You can use XOR gate and you can use the diode. Okay. Okay. So this is actually the mapping circuit. Okay. This is actually the mapping circuit. And it is also referred as encoder. No? Okay. It is also referred as encoder. Okay. So that is correct. Okay. It is an encoder actually. 2 to 4 encoder. And you can implement it using a XOR and diode, and there are many, and I think you can use it XNOR also. Okay, using the XNOR also you can implement this. Okay, so we are not going to focus on this implementation, but it is also uh, very simple implementation is there. Okay, so you can use the truth table, and you can construct the value. Okay. Okay. So you can construct the truth table and you can construct the value. Okay. So you have 4 output and 4 input and you have 2 outputs. For 2 outputs, you can you can construct the truth table and you can construct the logic circuits. Okay. So that is it. Okay. So what happened here? Okay. So I have given this kind, if I have given this kind of signal to the ADC, we have implemented. Okay. So you have 2 bits. Okay. And your value should be from 8 to 0. Okay. So first this ADC will sample this. Okay. With the sampling rate it have like this. Okay. So it is sample. Okay. And it get these samples. Okay. It get these samples and try to encode them into a binary value. Okay, binary value. Okay, so you can see that if you have 8 volt, then up to 6 volt, you will have some binary value. Okay, so all the voltage values we have to approximate. Okay, and here the other voltage value. Okay, less than 6 voltage value we have approximate to the 8 volt, that is called quantizing, and we can encode them. Okay, okay, and then so we have some bits here. Okay, and maybe if you consider this voltage level, maybe it is maybe less than 6. Okay, or greater than 6. If it is greater than 6, you have to quantize them to up to 6. Okay, if it is less than 6, you can quantize them to 6. Okay, then voltage 6 also you can encode. Okay, so other voltage level you can consider, and if it is also so you have to quantize it to the encodable value, then you can encode it to the binary value. Likewise, you can encode. Okay, so here also again you can use parallel to serial mapping, or you can use a multiplexer here, or you can use a shift register here. Shift register, we have talked about the shift register also. Then you can convert this parallel to serial. Okay, and you can get a waveform like this. Okay, so this is the digital to analog process, and this is how we implement the digital to analog uh, digital to analog conversion. Sorry, analog to digital conversion. Okay, so this is the analog to digital conversion process. Okay, analog to digital conversion process, and this is how we implement the analog to digital converter. Okay, so there are many implementation, but this may be the most simple implementation. Okay, so I think you are familiar with that one. Okay, so as a homework, try to do this one. Okay, example 2. Okay, so so if you have a 3-bit resolution ADC, so if you have 3-bit resolution ADC, okay, and if your maximum voltage, input voltage to the ADC, input voltage to the ADC, let's say that V max 8 volt, okay, and minimum, okay, minimum input voltage to the ADC, let's say that V min, it is 0 volt, okay. Now find how many voltage levels we can encode using this ADC. Okay, and what is the minimum voltage step we can identify this. Not we, this ADC can identify. ADC can identify. Okay, then implement this. Now, if it is 3 bits, you can represent 8 voltage levels. Okay, to represent 8 voltage level. Okay, and also you have to find what are the voltage levels. Okay, what are the encodable voltage levels? What are the encodable voltage level? Okay, and you have to get that one also. Okay, then you have to implement this. Okay, so you can have 8 voltage levels, encodable voltage levels. Okay, and so you have to compare it. With the voltage value, the input voltage value. For that one, you need to have 8 comparator circuits. Okay, so try to implement this by yourself as a homework. Okay, so I think you can do this one. Okay, you can do this one. Okay, And if I go back to the that website, okay. So here you can see that here you are using 3 comparators, okay. So actually that means, okay. So you can see that here we have used 4 comparators, okay. 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 And you can see if you consider the last comparator, okay. If you consider the last comparator, um, actually the last comparator we need to represent the lowest value, and that is equal to 0 actually, okay. Actually we no need to care about these values, okay. We no need to care about these values, and for this one we no need to care about this one, okay. And this one we no need to care about this one. This value we no need to care, okay. We have to care about on the needed one, okay, because we are not going to represent this we are not going to represent our voltage value using this combination, okay. We are just this is just the comparator value, okay, and we are represent this using these values, okay. Okay, so you can see that for the last value we need 0, okay. So it is already grounded, okay, it is already grounded in this circuits, okay. So that will not affected to the implementation, okay. So that is the things you should have understanding, okay. So you can see that that is already grounded, okay. And you can see that, okay, you can see that so this we no need to uh, worry, okay. This need no need to worry, okay. We have to worry about uh, these digits, okay, this digit and this digit, okay. And you can see that uh, at all time d naught is 0. So you have to consider 0 at this point also. In other point, whether you will have 0 or not, you it is not affected to your implementation, okay. So that is why this d0 is grounded, okay. So you can uh, so you can try to understand this one also, okay. But I think this is very clear, no, if you use 4 comparator and you consider this like this, it is somewhat uh, easy to understand, okay. But maybe this approach maybe has some confusion. Maybe you will have some confusion in this approach, okay. So you better go through that procedure, but it is up to you, okay. And here I think you have to, here also it design 3 bits 1, okay. But I think it is better not to go through this approach, and if you can use my approach, it may be easy, okay. So actually today I hope to do the ADC part also, okay. But DAC part also, but the time is not enough to go to that one, okay. So the things you have to understand is that, okay, so do this as a homework, okay. So next day we will start the DAC, okay, DAC implementation, DAC implementation, okay. Actually, this is somewhat simple than ADC, okay. You can use a resistor, you can use a resistor ladder, you can use a resistor ladder to to construct a DAC, okay, to construct the DAC, okay. So uh, this the implementation is very easy, okay. You have to use the Ohm's law actually. You have to use the Ohm's law here, okay. So we will discuss how to do that one, how to implement a DAC, Okay, in next week. Okay. Okay, so please do this one. Okay, for your exam, you will come this kind of maybe you will uh, you can get this kind of designing question. Okay, so please be familiar with that one. Okay, so shall we stop now? So if you have any question, you can ask. Otherwise, you can leave. Okay. So thank you for participating.
සර්
Yeah.
සර් ස්ක්‍රීන් එක මේ පේන්නේ නැතුව ගියා මේ අර මට එතන ප්‍රශ්නයක් තියෙනවා අහන්න.
Okay.
මේ අර සර් කලින් පෙන්නපු මේ PDF එකේ අර මේ කම්පැරේටර් එක දාලා තිබ්බේ මේ දැන් අපි සර් හදපු එකේ තියෙන 8 වෝල්ට් එකටම දාලානේ උඩටම පළවෙනි කම්පැරේටර් එක රිෆරන්ස් පින් එක අරකේ තියෙන 6 වෝල්ට් ඉඳන් දාලා මේ එතකොට කෝකද සර් වැඩියෙන් සාමාන්‍යයෙන් භාවිතා
නෑ ඒක ඔයාලට දෙන ස්පෙસિෆිකේෂන් එකත් එක්ක. ඒ කියන්නේ එක දැන් ඒක ඇත්තටම මෙයාගේ මේ ඔප් ඇම්ප්ස් එකේ තමයි පවතින්නේ. සමහර ඔප් ඇම්ප්ස් වලට හයි වෝල්ටේජ් සපෝට් කරන්න පුළුවන්. හරි. එතකොට
එතකොට අර මේ අපිට 6 ඉඳන් 8 වෙනකන් මේ අවුට්පුට් එකක් ගත හැනේ එහෙම දැම්මම නේද?
මට තේරුණා ඒක.
දැන් මෙතනදී අපි හදපු විදිහට 8 වෝල්ට් වලට අවුට්පුට් එකක් ගන්න බෑනේ.
8 වෝල්ට් වලට අවුට්පුට් එකක් ගන්න පුළුවන්. දැන් අපේ එකේ 8 වෝල්ට් වලට අවුට්පුට් එකක් ගත්තා. ඒකේ මේ තියෙන 1110.
හරි.
හරි. 8 වෝල්ට් වලට රීප්‍රසන්ට් කරන්න පුළුවන්. 8 වෝල්ට් කියන්නේ ඩිකෝඩබල් වෝල්ටේජ් ලෙවල් එකක්. ඩිකෝඩබල්
D4 එක හැම වෙලාවෙම D4 එක හැම වෙලාවෙම 0 නේ 8 වෝල්ට් ගත්තාම මේක මට මේ ප්‍රශ්නේ තිබ්බේ. අතන අර විදිහට ගත්තාම ඒකත් එක වෙනවනේ කොයි වෙලාවක හරි.
මිනිමම් එක 0. ඔයාලට කොම්පියුටර් 0 આવොත් එන්නේ 00 වෝල්ටේජ්. හරි. ඒ කියන්නේ 0 ඉඳන් 2 වෝල්ට් වලට යනකම් හුඟක් වෙලාවට ඔයා රීප්‍රසන්ට් කරන්නේ. ඒ කියන්නේ ඩැක් එකෙන් දෙන්නේ 0 වෝල්ටේජ් එක. හරි. ඊළඟට 2 ඉඳන් 4 වෙනකල් sorry. ඔව් 2 ඉඳන් 4ට ඒ කියන්නේ 3.99ට යනකල්ම ඔයාට දෙන්නේ 2ට අදාළ වෝල්ටේජ් එක. හරි. ඊට පස්සේ 4 ඉඳන් 5.999ට යනකල්ම ඔයාට දෙන්නේ 6ට අදාළ 4ට අදාළ වෝල්ටේජ් එක. 6 ඉඳන් 7.99ට යනකල්ම දෙන්නේ 6ට අදාළ වෝල්ටේජ් එක. 8ට එක දෙන්නේ ඊට පස්සේ 8 එක දෙන්නේ. හරි?
හරි.
ඔය විදිහට තමයි ඉන්නේ. හරි? එතකොට ඒක ඉම්ප්ලිමන්ටේෂන් කරනකොට සමහරට ඔක වෙනස් වෙන්න පුළුවන්. හරි? එතකොට ඒක එක එක ඉම්ප්ලිමන්ටේෂන් වලට වෙනස් වෙනවා ඒක. දැන් එතකොට ඔයාට මේක ඇත්තටම මේක කරන්න ඔය කට්ටියට කොහොමද මේ ADC එකක් බේසිකලි ඉම්ප්ලිමන්ට් කරන්න කියන එක පොඩ්ඩක් ඔලුවට යන්න. හරි? එතකොට ඒ අයිඩියා එකෙන් තමයි මේක කරන්නේ. එතකොට මේක එක එක විදිහට ඉම්ප්ලිමන්ට් කරා හැකියි. අපිට ඉම්ප්ලිමන්ට් කරන්න යනකොට පොඩි පොඩි කෑලි ඇඩ් කරලා අපිට ඕන විදිහට මේක කස්ටමයිස් කරගන්න. හරි? එතකොට ඒක ටිකක් ඇඩ්වාන්ස්. ඒ කියන්නේ මහ ලොකු දෙයක් නෙවෙයි. පොඩි පොඩි රෙසිස්ටර් දාන්න තියෙනවා. මේවා දාලා කරන්ට් ටික ලිමිට් කරලා වෝල්ටේජ් ලිමිට් කරලා අපිට මේ ඉන්පුට් වෝල්ටේජ් ලෙවල් අපිට වෙනස් කරගන්න පුළුවන්. හරි? දැනට ඔකට මේ විදිහට මේ ඔළුවේ තියාගන්න. තේරුණාද? හරිද? ඔයාගේ ප්‍රශ්නේ හරිද? උත්තරේ හම්බුණාද? Right, okay. Thank you.
හරි සර් thank you.
Hari, okay. Okay, so if you have any question, you can ask. Okay, otherwise you can leave.